Saxon Algebra 2, Lesson 18. We're following John's tried and true format of an algebra topic and then a geometry topic. The old 1-2 punch. We're going to start with the ratio word problem. I want you to remember that a ratio means a fraction. It's two numbers that are being compared and we write them as a fraction. A proportion is an equation with two ratios. All right, so it would be like A over B equals C over D. Ratio equals ratio. This is a proportion, all right? So a ratio is one or the other of them. A proportion is when you set them equal to each other. In these ratio problems, we will be creating ratios and then we will solve them by setting them up as proportions, all right? Let's look at an example. The ratio of Arabians to mixed breeds in the herd was 2 to 17. If there were 380 horses in the herd, how many were Arabians? It's a horse problem. You guys know Vivian Rice. She's a horse lady, right? So I'm thinking of her. The key to setting up these problems is something that John doesn't know how to do, and that is make what one of my students used to always call a tic-tac-toe board. Whoops, 18.1. In our tic-tac-toe boards, we'll always have two columns. We need as many rows as we have different things we're comparing, plus one more. In this one, we're comparing Arabians to mixed breeds. So here's what I do. I have a row for the Arabians, I have a row for the mixed breeds, and then I need one more row because Arabians, I'm just going to write A. Mixed breeds, I'm just going to write MB. And in the last row, we're going to write the total. We always want to add a total line now. All right? In the first column, we're going to write the ratio information that we get. And then here, John's going to tell us about the actual situation we're dealing with. And we're going to use this column to record that. Now, the first time I read a problem, I'm not really trying to focus on the details. I'm just trying to understand what kind of a problem it is. Then I get myself organized. Then I go back in, find the numbers, pluck them out, and drop them in. You probably already do the same thing, but I just want to make the point that it's very intentional the way I do that. The first time I read the problem, my brain really is just going blah, 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 blah. I don't even know what this means. All I'm looking for is the pattern, the type of problem that it is. Then I set myself up and get organized. Okay. Ready? Here we go. The ratio of Arabians to mixed breeds in the herd was 2 to 17. Just write it right down in the ratio thing. That's the fraction, 2 to 17. We could write it as 2 over 17, and soon we will. If there were 380 horses in the herd, okay, that's the actual number. How many were Arabians? So that's where we put the X. All right? Now, in order to do this problem, what we have to do is we have to add those together to get the total. We can always add that. So we can always complete this line. And we need to know about these 17 mixed breed horses simply to get that total. Now, we're not concerned with them. They're not part of our problem. We're trying to find out how many Arabians are in our actual herd, knowing that 2 out of 17, no, the ratio of Arabians to mixed breeds is 2 to 17. That means 2 out of 19 in the total herd are Arabians. Using this chart, we can now easily set up a nice little proportion. This is the ratio of Arabians to total in concept, kind of. This is the actual herd. And now all we have to do is cross multiply to solve. Okay, and let me write that up here. Whenever we're dealing with proportions, we cross multiply to solve. So, but watch how I do it. 2 times 380 equals 19x. I do not want to multiply 2 times 380 because I'm hoping that 19, which I'm going to divide both sides by, I'm hoping that 19 is going to go into this. I don't want to make the pieces bigger because I'm trying to cancel. So I want to just leave this as is, and then I'll simplify and write a final answer at the end. That cancels. And see, this helps me. I know that 19 times 2 is 38. So I know that if I cancel this against this, it must be 20, right? That's why I don't want to multiply. I want to see the pieces of the numbers so that I have a better vantage point for canceling. So now I can say that x equals 2 times 20, 40, and when there's words in the problem, we want words in our answer, 40 Arabians. What's the difference between an Arabian horse and a mixed breed? I'm not sure. Let's ask Vivian. If next time you see her, say, Vivian, please enlighten me. Okay, that's the first example. Ready for another? How many are there? Just 2. This is our second ratio word problem, second and final. All right, here we go. It took 600 kilograms of sulfur to make 3,000 kilograms of the new compound. How many kilograms of other materials would be required to make 4,000 kilograms of the new compound? Blah, 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 blah. The first thing I have to do is push past the fact that this is a chemistry problem. That makes me start to think, oh, this one's going to be harder because it's about chemistry and math. The other one was just about horses. They neigh and whinny. That doesn't bother me at all, but chemistry freaks me out. John does it this way for a purpose, you guys. What he wants us to remember is we don't have to let the chemistry freak us out. It doesn't have to be any more fearful than our friendly little Arabian and mixed breed horses. So let's try it again. And this time we'll look, well, we know it's a ratio problem, but we have to make sense of it. So let me help you make sense of this by giving you just enough chemistry information to be dangerous. It says it took, we had some sulfur. Let's put it in a little chemistry dish. And then we had something else and we added them together and we got what John is calling a new compound. Compound means things that are combined, right? So we don't know what was combined with the sulfur to get this new compound, so we're just going to call this other. We don't know what this thing is. But what John tells us is that there's a ratio relationship. So again, I'm going to make a chart. I'm going to have 2 columns, and I'm going to have 1 row for the sulfur, 1 row for the other, whatever that means, and then 1 row for the total. Sulfur, other, total. This is the ratio relationship, and then this is the actual number in our situation. All right, it took 600 kilograms of sulfur to make 3,000 kilograms of the new compound. Oh, okay, so this helps. This is what we're talking about here. How many kilograms of other materials would be required to make 4,000 kilograms of the new compound? Okay, so everything's being measured in kilograms. We don't have to worry about that. What we have to figure out is if we had 600 units, if we have 600 units of sulfur and we ended up with 3,000 units of this compound, that means this must have been 2,400. It has to add to 3,000, right? That is super helpful. Now we see, okay, we don't need this row. These are the 2 rows and columns that will give us the proportion we need. So we say 2,400 over 3,000 equals x over 4,000. Right? We just lift them off and drop them into the proportion. We don't have to think about this at all, okay? It always works that way. Now we're ready to cross multiply 2,400 times 4,000 equals 3,000 times x divided by 3,000. Beautiful, looks good, right? All those zeros, okay. Again, we don't want to multiply that because that's going to make canceling way harder. So the first thing I'm going to do is I'm going to divide top and bottom by 1,000, which basically means I'm crossing off the zeros, right? 4,000 divided by 1,000 is 4. 3,000 divided by 1,000 is 3. So crossing off the zeros is the same as dividing by a power of 10. Okay, so now I have 3 and 4. 3 goes into 24 8 times. So now my bottom is down to 1. So now all I have to do is multiply 800 times 4, which gives me x equals, there's the 32 of the 8 times the 4, and then 2 more zeros. And I'll put a unit on there, kilograms. That's our final answer. That's how many other materials we'll have to use in this batch that we're trying to make. Beautiful. Okay, we're going to switch to what seems like another topic. We're going to talk about similar triangles. But the cool thing is we're still going to be talking about proportions and cross multiplying to solve. And here's what I want to tell you. Similar triangles are triangles with special properties. Their angles are the same, exactly the same, but their sides are different lengths. Okay, that's the definition of a similar triangle. Same angles, different sides. But a cool thing about the sides is that they are proportional. Ah, there's the proportions again. So that means we can create proportions between big triangle, little triangle, this side and that side, and we can solve for the missing sides. Cool. So there are 2 ways to solve these kinds of problems. The first way, as I just mentioned, is to use proportions, which leads you then to cross multiplying. That's not bad. That's what we were just doing in those ratio problems, right? The Arabian horses and the new compound. This makes sense. The other way is to use something called a scale factor. And John uses this kind of abbreviation to mean scale factor. Oh, he puts an arrow on it because that arrow is important. Now, here's the thing. I think scale factors are needlessly confusing. The math is exactly the same. You're just using proportions. You're just creating a fancy proportion and giving it a name. But the symbol is confusing and the name is confusing. I don't like scale factors. Boo hiss. I much prefer for my students to use proportions to solve these problems because that's exactly what we're using in other problems. So let's not change it and make it weird just because it's geometry. Let's leave it the same and use the same method. So John goes back and forth. I will always use the proportions method, and I recommend that you do too. All right, 18.3. And if you ever are taking like some sort of placement exam or you're taking another class and your teacher tells you you should do scale factors, come to me. I'll explain you how to do them in a hot minute. They're not hard. They're just needlessly confusing when proportion is so easy. Okay, so we have two triangles. I'm going to draw the picture first. Then we can read John's lovely narrative to us. Now, similar triangles should always look the same. Sometimes you have to spin them to get there. They usually have a big and a small and a big. And we see a lot of markings on them. So I'm going to start copying them. Oh, and I notice, okay, so those angles are the same. There's our 2-line tiki. And here's a 3-line tiki. Okay, so what does that tell us? That tells us the angles are the same between the two triangles, though we can clearly see one is bigger and one is smaller. Mine look kind of the same size. If you look in the book, you'll see they look different. Okay, so that gets our brain going, oh, these must be similar triangles. This is our brain thinking. And then we also, as soon as we think that, we think, oh, we can set up proportions. Yay. Okay, so that's where we're at so far. Let's put the numbers on. We have numbers too. 4, 7, 5, 3, x, y. And now I look at the instructions and it says the tick marks tell us that these two triangles are similar. Yeah, we figured that out. Find the scale factor and then find x and y. I hereby give you permission in your homework to ignore John's instructions and pretend that that says use the proportion method to find x and y. All right? So the first step in using proportions to solve similar triangles is to find what I call the anchor proportion. Now, John doesn't use this expression, so you heard it here first. Let me tell you what it means. It means that as we compare matching sides between the two triangles, we notice that some of the pairs of corresponding sides have a number compared to a letter. Those are not our friends. Those are the problems we're trying to solve. But one pair of sides has number in number. That is our anchor proportion. And the way I would describe this in non-mathematical terms is that there are numbers on both matching sides. Right? There's a number here and there's a number here. That's what I'm trying to say. Now we use that it shouldn't, well, okay, never mind. I'm not going to say that. Okay, so we know that this triangle compared to that triangle is going to be 4 to 3, and then we can compare it to 5 to x, right? Big triangle this side over little triangle this side equals big triangle this side over little triangle that side. See how they match? So that's the way we always want to set these up. Now we're ready to cross multiply. We get 4x equals 15. These numbers are so small I go ahead and multiply them. X equals 15 over 4. That is an incredibly unsatisfying answer, but it is correct. Now to do the same thing to solve for y, we once again use our anchor proportion. 4 over 3 equals, and this time we'll do 7 over y. Okay? And we do the same thing, 4y equals 21. And we get y equals 21 over 4. Those are the correct answers. So we just use the anchor proportion and solve. what I was going to say before, but I didn't want to confuse you. I guess I'm willing to confuse you now. I told you at the beginning that the ratio was the fraction, and it's when we make the equation that it becomes a proportion. And then I went and referred to this part of it as a proportion. I should be calling this the anchor ratio, right? Technically, that's not a proportion, it's a ratio. I've been calling it that for years, and it just occurred to me how wrong I was, okay? But either way. Okay, there's only just the one problem there, so we are done. I'm just taking a quick look at the homework. This time it says find A and B, but we can see from the tick marks that these two triangles are similar and they're lined up perfectly. Later, John's gonna confuse us by like twisting one of the triangles so that we have to mentally untwist and get them the same again, but he's not dealing us that card yet. He's being nice. All right, so this is just like the problem that we did. Find your anchor ratio and then go from there to build proportions to solve. Okay, I hope this all makes sense. It feels like it makes sense for me, but I'm not you. Okay, thank you, goodbye.